Okay, everybody, welcome back. Today we're going to talk about Ohm's law and electrical. Okay, guys. So what is an atom? Okay. What's an atom? Atom is the smallest unit that makes up matter. Two atoms combines together make water. For example, two hydrogen atom make one oxygen, H2O. Atom made up of three things: electrons, protons, and neutrons. Electrons, negative charge; protons, positive charge. I'll cover that. P and N, I'll cover it in a second. Neutrons are neutral charge. So let's put in the pictures, make it easy to understand. Electrons orbit the nucleus. As you can see here, the blue is electrons. Inside the nucleus, we have the protons and the neutrons. Okay, cool deal. Electrons are negative charge. Positive charge are the protons. Easy to remember, P and N. Protons positive, P positive. Neutrons are negative and N negative. Therefore, neutral is taken, positive is taken. Therefore, electrons are negative. Easy to remember. This is important because we are in this is electricity, flow of electrons. The atom has many shells, different size and form, atomic number, but we don't care. All we care about is the outer layer. I'll cover that in a second. Helium have 2 electrons. Neon have 10. Potassium have 19. Okay, all we care about is 1 electron because electricity moving of electron. All we care about the 1 electron in the outer shell, outer layer. Okay, the copper atom has 29, but what's more important is only 1 in the outer layer because electricity is the movement of electron in a conductor. Because we only have 1 from outside, easy to move electron. You get 2 metal pieces together and rub them, my soda can, screwdriver, I can move electron easy. I cannot move it on the table because it's wood. All right, let's move on. Electrons do not travel in insulators. That's next. Oh, no, I'm sorry, after that. The most effective electrons: silver, gold, copper, aluminum, and mercury. Other strong conductors: platinum, brass, bronze, graphite, and dirty water, and lemon juice. Clean water is an insulator. Now, insulators, they have many electrons in the outer ring. We cannot add or remove anymore. Make sense? Insulators do not conduct or transport electrons, move electrons. And you can see here, this insulator have 5 to 8 electrons in the outer ring. What's important? All we care about: 1, 2, 3, 4, 5, 6. This one have. Let's move on. The fluorine, all these are insulators because they have how many? A lot outer ring: 7, 6, and 7. Fluorine, chlorine, and bromine. Fancy word. Anyway, so make sense? Okay, let's move on. All these are here. We have no flow. Insulators have many electrons. We cannot add or move anymore. Good insulators are rubber, glass, pure water, oil, air, diamond, dry wood, dry cotton, plastic, and asphalt. Other insulators: fiberglass, dry paper, I don't know how to say that, chromatics, and quartz. Okay, so in here, electrons are not moving because they cannot break apart. They're combined together. All right, this is important because we have to understand the flow of electrons. Now, move on to the flow. We have to learn about the atom first before we learn electricity. 3 things we need to move electrons: power source, a battery. Many ways to generate power. This is a different subject about power source. We need a path. We need a path to move the electrons, like the car need a path to move on the road. In this case, the copper wire is the path. And of course, we need a load. We need a resistance. No resistance, we have problems. I'll cover that in a second. Alrighty. Now we have something called short circuit. No load, big problem. We need resistance to slow down electrons. Do we jump barely together? No, there's no resistance. Boom, electrons fly so fast, creates heat. Boom, explosion. We need resistance because short circuit is called short circuit if we have no resistance. We need resistance, he said in the movie, that movie Outbreak. Makes sense. Make you remember what resistance is. Resistance coming out of the helicopters. Okay, let's move on. Or the police don't resist arrest. Okay, let's move on. Open or closed circuit, important terms in HVAC or electrical. Open circuit, no path, no flow. Closed circuit, path, flow. Air conditioning, refrigeration terms. You say the circuit is open, the unit's not running, we have open circuit or closed circuit. Important to know these terms. Okay, open circuit, short circuit. Open circuit, no path, no flow. We have voltage, but no path for the electrons to flow. Electrons are just moving around the wire in random, no place for them to go anywhere around other atoms. Okay, but there's no place to go unless we have a path. All righty. Short circuit is when we have short circuit, no resistance, no flow. Path goes to the least resistance in everything. Very important to understand in electrical. Many machines I fix, nobody else could, because I have very good knowledge of electrical theory. Path goes to the least resistance. If I am electron, why in the world I want to go into a big resistance light bulb? I'm going to go easy path and go straight back to neutral, back to positive, excuse me, negative to positive. Okay, let's move on. Ohm's law. They make it so confusing, man. EA ohms, volt IR, EIR, BD. I'm going crazy. I'll make it easy. That's why I'm here. Okay, Ohm's law. Ohm's law is a formula to calculate the relationship between voltage, current, and resistance in an electrical circuit, shown below. Voltage measured in volt, and it's the electromotive force, the E, also known as EMF. Current, also known intensity, measured in amperage or ampere. Resistance measured in ohms, omega sign. Okay, now note, we have two EMF. Electromotive force is EMF, that's the voltage. The electrical pressure or the force to move electrons, voltage. But we also have electromagnetic field, EMF. The invisible shields go around a conductor. I'll cover it more when I do the transformers, relays, contactors class, and coils. It's important to understand EMF also, but this is Ohm's law. That's another class for another subject. All right, Ohm's law. Voltage measured in voltage is a measurement of the electromotive force which is E for electromotive force. Resistance is the measurement of is measured in ohms, and current is the intensity measured in amp. Okay, same thing here. Make it easy. Think of 10, 5, 2. 10 times 5 times 2 is 10. 10 divided by 5 is 2. 5 times 2. Okay, and that's how make it easy. 10, 5, 2. We all know the simple division and math. The top number, the volt, is divided by the lower numbers, and the two lower numbers multiplied by each other. The two lower numbers multiplied by each other will give us the top number, and the top number divided by the bottom number will give us the other bottom number. 10 divided by 2 equals 5. 10 divided by 5 equals 2. 5 multiplied by 2 equals 10. Okay, that's easy to remember. 10, 5, 2. Now, let's move on and do examples. Make you understand what Ohm's law works, relationship between voltage, amperage, and current. The horse is 10 volt. Okay, one horse have a force of 10 volt. Alrighty, the road is resistance, and that's 2. Therefore, one horse will pull the carriage 5 miles per hour. Why? Okay, because we know 2 is the road, and one horse have a force of 10. 10 divided by 2 is 5. So we know the horse is going to go 5 miles an hour. Makes sense? 10 divided by 2 equals 5. Next slide. If voltage goes up, intensity go up. If voltage goes down, intensity go down. So if I increase the horsepower, it's going to go faster. The flow will go, intensity goes up. If I decrease the voltage, then it's going to go down. Resistance is the road. Intensity is the speed. Electromotive force is the road. Is the horse. Okay. Now, we have 2 horses, 10 volt and 10 volt. Give us 20 volt. Therefore, now what happened? First slide. 10, 5, 2. Now we are 20, 2, 10. 10 divided by 2 is 10. Now we doubled the mileage. So we doubled the horsepower, we doubled the mileage. Makes sense by using Ohm's law. Note, 2 barrels in series increase the voltage. 2 barrels in parallel increases the amperage. I'll cover that more when I do series and parallel circuit and how apply to the HVAC system. This is about Ohm's law. Okay, now we have half a horsepower or baby horse. What's going to happen now? Go down to 2.5 miles an hour. Okay, makes sense. I hope it makes sense now. On top is 1 horse, 10 volt is the horsepower, divided by 2 resistance of the road equals 5 speed. Down here we have half a horse. So 5 divided by 2 is 2.5. 5, okay, voltage goes down as intensity go down. And that's 1 horse, 2 horses, and half a horse, 1 big slide together. As you can see, as the voltage increases, the current increase. Now, the road goes down. 1 horsepower still have the same horse, but resistance goes down. So look what happened now. We are dividing by 1. 10 divided by 1 resistance equals 10 amp. Resistance went down by 1. The speed increased. Resistance went down by 1 step. Resistance doubled. Went up by 1 step. From 1 to 2 to 10 to 20. Right, from 5 to 10, excuse me. Right, makes sense? Okay, now next slide. Oh, where is it? Oh, I missed it there. Down. Up. Now went up. So now the road has resistance of 4 instead of 2. Right? So therefore now it slows down the horse from 5 miles an hour to 2.5 miles an hour. Okay, this is all theory now. This doesn't happen practical. Let's move on to heaters. These are heaters. This shows how the voltage increase. Next slide. 120 volt and 240 volt. Look at this. We double the voltage. We double the flow. 10 ohm heater at 120 volt give us 12 amp. We double the voltage here, 220, give us 224 amp. Okay. The more resistance, the less the current intensity. Look at that. Now, this was a little confusing. It's important to know. The slower the electrons move, the less heat. The faster they move, the more heat. Electrons are, look at now the small window. Electrons got to flow between this finger and this finger, right? Now we have very long distance like this. It's going to take a long time for them to go from here to here. It's going to create low heat. We have shorter distance. Goes faster, creates hotter heat. So heaters that use more energy, produce more heat, have less resistance for more flow, more heat. The faster the flow, the faster the current, the faster the heat. Okay, now we have open circuit, broken. Open circuit, no flow, no current. And then if we have short circuit, here we go again, like jumping a battery, short circuit, fast flow, trip the breaker. Ohm's law only works in resistive loads. It doesn't work if it's inductive. Heaters, old lights and resistors are different than transformers, motors, and solenoids. But I'm using the example of a light, of a fan, because fan is a great example. You can understand how it works. It's harder for the electrons to go in a long coil with a fan. Again, long coil like this, it's going to take a long time for this fan to spin, makes it go slow. But now I have a small wire, a small winding on the motor. It's going to spin fast and go. This is important to understand because later when I cover compressor, run winding and start winding of the compressor, we know why the run winding is a lot smaller, usually 1.2, 1.5, than the run winding, which is way larger. That's later on when we cover compressor and compressors windings. But it's important to understand that a motor with a fast speed motor have less resistance than a slow speed motor. Okay, let's move on. Now, voltage in water. If the voltage or the force electrical pressure, voltage increases, the current will increase. All right. Example, we have water, no pressure, no flow. Normal pressure, normal flow. If we have less pressure in the hose, we will move less water, less current, less flow. More pressure, more flow. Makes sense? Same thing with electricity. Okay. Another example with the stadium. We have here A, we have no path, no flow, no current. The cars are the electrons, river is the resistance, bridge is the path. Nothing happening here. A lot of resistance. We have low current, very few cars moving, very slow. Less resistance, more current. The bridge is bigger, right? Bridge is bigger now, more path. The bridge is larger now, even more current. But if you have no bridge, somebody messed up and did not made the road very, very big, you also have too much flow, short circuit. This example is not too good. Okay, now let's move on to the wire size. Okay, the size of the water. Again, I go back, size of the wire comparing to water. 2-inch pipe will move water, more water than 1 inch, right? It's simple. More pressure, more flow, but water pressure doesn't change much. Okay, now 2-inch pipe will break if you have more than 52 gallons. 1-inch pipe will break if you have more than 9 gallons. But water pipes are rated on gallons, not pressure. Makes sense? Because water pressure doesn't change much, guys. Always water pressure about 80 to 120. Okay, that's normal. Up in the casinos and high rises, the pressure is higher because you're gonna pump the water up high. Sometimes the problem is with the ice machine because too much water pressure. They have a water pressure regulator on the upper levels because too much. Anyway, but for now, water pressure is only about 80 to 120. No big deal. Okay, but in winter, summer it changes a little bit. So it's not an issue about water pressure. What's the size of the pipe of the water have to do with how much gallons it's gonna carry. Same thing with the electrical people. Okay, the size of the wire have nothing to do with the voltage it's in it, the pressure. It have to do with the current it's moving. Okay, the number two wire will easily move way more electrons than number 18 wire, 2 and 18. Okay, the more pressure, the more flow, of course. Number 2 wire will break if the current will burn if the current is 95 amp. Number 18 will burn if the current goes more than 7 amp. Doesn't matter. Wires are rated on amperage because electrical pressure, the voltage don't change much. A little between summer, winter. You know, in summer, people use more air conditioning. I hope this makes sense. So now let's go back here to this first. I don't have the slide here. Let me pause here for a second, take a break, come back. Pause. Okay, guys, I am back. Animation and slideshow. Oops, not from the beginning. Oops. Okay. Sorry, I had to take a little break. Okay, let's continue with this. We were on the wire, and the wire have to do with the size of the wire, the thickness of the wire have to do with the current flowing through it. Because the voltage doesn't matter. It does to a point, but I have worked in, let's go to the wire size. My apologies. Good review. Okay, wire sizes here. Okay, so wire sizes. It shows here the amperage. Most homes have 20 amp right here. Most homes will use 12 amp. For the air conditioning, we're going to use 30 ampere, number 10. All righty. Okay, but one time I worked on 440 volt 3-phase, and it was only pulling 4 amp, and it had number 12 wire, which is, wow. But again, it doesn't matter what voltage it is. It's the current what matters when it comes to wires. Okay. Now, What happened if everybody flushed the toilet at the same time, right? We lose water pressure. What happened if everybody turn on the AC at the same time? We lose electrical pressure. It's important. Another way looking at it is Mr. Ohm, Mr. Amp, Mr. Volt. What happened if the ohms gets bigger ohm, right? Bigger ohm, less flow, right? The more the resistance, the less flow. Up there on top, the Mr. Ohm is small, so cannot hold less resistance, more flow. This is easy to understand, I hope better. Another example is the voltage. We have more voltage, more flow, less voltage, less flow. Okay, easy peasy. All righty, now let's move on to Watt's law. Watt's law, it measures the rate of the electricity consumed. Volts times amp is watt. That's how they know to charge you. All righty, now let's move on. I have to apologize. My voltmeter is broken. Look at this. Well, my voltmeter is completely broken, but I know this stuff works. I did it before. And this is a little toaster right here. Okay, it makes waffle. So my waffle toaster here, it says 120 volts, 60 hertz, 600 watt. Will cover the hertz in another class. But 120 volt, we know it's for sure. 60 watt is for sure. So the current should be 5. Why? 600 watt, I know. 120 volt, I know. Therefore, 5. So if my voltmeter was working, I guarantee you, I'll put on the clamp meter right here. I run the wire right here. It should say 5 amp, give and take. But it's broken. I apologize. Make sense? Now, why is this important to know? Because it's important to know how many can I plug these in. All righty? And what's the resistance of this baby? Resistance right here on the plug. It should be 24 ohms. Because we have 120 volt and it's 5 amp, it should be 120, 24 ohms. The same thing here on top, example, the computer will give me example. If you plug a heater 120 volt and it draws 10 amp, then what's your wattage? How much energy you're using? 120 volt times 10 amp, 120 watts. We also have series and parallel circuit, and we have 3-phase. Next video I make about series and parallel circuit, and they use an HVAC, and AC/DC, power distribution and transformers, 50, 60 hertz the frequency, single and 3-phase, 120, 208, 230, and 240 volt, 240 single phase, 240 3-phase, 24 volt. That's another class to talk about another time. A lot to learn in HVAC. Okay, guys, thank you very much for today. Any questions, leave in the comments. Let me know how this video went. I'm sorry my damn meter is broken, but trust me, it's correct. Okay, guys, and it's important to know the voltage. Let's finish on the story. Good, yeah. In China, my buddy brought his hair dryer and it burned because the voltage over there is 220 volt. Well, here in America, it's 120. If you buy the little plug from Walmart, international adapter, yeah, it plugs in, but it's not the right voltage and not the right frequency either. In Europe, it's 50. The rest of the world is 50 hertz. We are 60 hertz. I'll discuss that in the AC/DC class and the power distribution and transformers class, another class for another time. This is Ohm's law is good enough for now. Thank you, and let me know how you like this video. Peace.